Welcome to the class, and what we are going to discuss today is this CRC interleaver. What are the ideas, why is it there, okay, and how is it implemented. So we have been discussing this PDCCH chain and the key components of it. This is basically the CRC interleaver principles are again there from the same papers. Okay. So what have we looked till now? DCI, CRC gets attached, 24-bit CRC, right? Then last 16 bits of the CRC are scrambled, okay? Then there is this CRC gets interleaved, okay? Right? And that interleaved data is basically fed to this polar encoding, okay? So what I say is CRC interleaver, basically the whole of this gets interleaved, okay? The name is given as CRC interleaver, the data gets interleaved. Then, what is this? The polar encoder is working as the interleaved data, right? Okay. Then again after that there is sub-block interleaver. There are different interleavers, okay, we'll see why they are there, why this is also. Then other blocks we are comfortable with, we'll come back to it, but what is happening here, if you look at the reverse of it, receiver chain, what is polar decoding going to work at? It's going to again work with on the interleaved data, okay, the data which was interleaved here. And only after that it is de-interleaved, okay, right? So again, designed to reduce the pain of line decoding or the complexity of line decoding. Okay, let's use a more technical term now. The complexity is basically has to be reduced. Okay, so let's see that. Okay, so we'll first talk about these principles and then we'll see why it is, how it is done, why it is done. Okay, I'll explain all this to you. Okay, what is happening? Basically, this is the paper I've used. Okay, for understanding this principle. CRC interleaver is designed such that after interleaving, okay, what am I saying? This interleaver is designed in a particular way, okay? The CRC interleaver, what are we saying here? Each CRC bit in the interleave sequence depends on the information bits that precede it. Okay, what are we saying here? That you have calculated the CRC, okay, right? So the input plus CRC, okay, goes inside the interleaver, okay. Now the output will be interleaved, okay, and the interleaved output will be such that each of the CRC bit, okay, in the interleaved output sequence depends only on the information that precedes it, okay. So just look at this, okay. So what are we saying here? If this picture will make it clear, okay, this sentence, what I'm saying here, for example, first CRC bit P0, okay, the polynomial, okay, the CRC polynomial which calculates the CRC, okay, the output depends on the polynomial, okay, and what is it? If you remember, in the polynomial is some sequence, okay, and the CRC which is generated, okay, is a function of the input and the polynomial, okay, and that polynomial decides which input bit will create that CRC bit. We did not discuss from that perspective, okay. What are we saying here? I just gave you a recipe for creating this CRC, okay, right. So if you look at the CRC also, what are we doing here? We are dividing the input by the polynomial, okay, right, and the polynomial has certain, what does it do? It has certain delays, okay, right. It takes in, so it basically takes in those message bits, okay, and then process them. That's a broader idea, okay. So each CRC bit which is generated is basically a function of certain input bits, okay, right. There was no need to tell you there, so I did not tell you, okay. Now it is coming here, okay, so I have to tell you that. Just to look at this, okay, for example here, okay, this is the CRC bit, okay, right. So this is basically what are we doing here? This is 24-bit CRC, okay, this is the message. Okay, right? A0 to A11 is a 12-bit DCI. Okay, we are appending 24-bit CRC to it. Correct? Okay. Now, what am I saying here? This parity bit P0, okay, depends only on the information bit A1, A4, A6, A10, and A11. That's how it is generated. That's how the CRC polynomial is, right? Okay. Please understand this. What am I saying here? That this CRC bit is generated only from these information bits, okay. We did not talk about this aspect earlier because it was not required, okay. Now that it is required, we are bringing in, right. So P0 depends only on this, okay, right. This is the first parity bit, correct. This is the input sequence, this is DCI plus the CRC. Now it interleaves It has to go through undergo the interleaving. Okay. Now interleaving can be designed in an arbitrary way. Okay, but here it is designed in a very sophisticated way. Okay, what are we saying here? That's what it makes sense. Okay, this P0, okay, after interleaving, okay, it will come after this. The way you will see that in the output sequence when you finally interleave it. Okay, this is the input and this is the interleaved out. Look at where this P0 is coming after interleaving. Okay, where is it coming? It's coming after. Okay, these bits also get interleaved. Okay, this DCI bits are also getting interleaved. This bit is going here. Okay, right? You see this parity bit doesn't depend on A0. This CRC bit doesn't depend on A0. Okay, that's okay. What are we saying here? CRC bit depends on A1 to A11. Okay, right? And each of the CRC bit is interleaved, or all these bits are interleaved such that this is applicable. So what are we saying here? P0 depends on this. Okay, P0 comes here. All other bits are coming on which it is depending after interleaving. It is coming before this. Okay, if you don't design it, okay, properly, what could happen? This bit could go after this also because it's an interleaver, right? You are interleaving the bits. This bit could go after this also. I'll tell you what role it plays. Okay, plays a crucial role in polar decoding. But first, understand this key idea, right? So if this parity, for example, this P1, I have not given you this where it depends on. It will depend on only on these message bits. Similarly, this bit will depend only on these message bits. Okay, right? That's how they are interleaved. Fine. Okay, so that's the idea. That's the key constraint we are imposing. Do we understand this? What am I saying here? This CRC bit will not depend on any of these message bits which are coming after that. Okay, P1 can depend on this, not P0. Fine, okay, right? So this, do we understand this? What are we saying here? This idea is used to reduce the PDCCH decoding complexity. I'll tell you this little later, okay, right? So actually it's coming now. So this polar decoder decodes information and CRC bits at a time in their interleaved order. That's what did I say? Okay, polar decoder is working on the interleaved bits, right? Now, so what will happen here is polar decoder will give you these bits, will give you parity bit also, okay? Now, there are these algorithms which can basically, what will happen is, you have this parity bit, or you have this CRC bit, okay, P0 we are writing, I am telling it parity, it's CRC, okay. What am I saying here? This CRC bit has come, these message bits have also been decoded by the decoder at the receiver, okay, right? What will happen is, okay, this CRC bit can be validated by the receiver. Okay? This scramble bit can be validated. Okay, there are algorithms to do that. Okay? If this is not validated, what will receiver do? It will immediately stop this decoding because the first bit itself is not matching. Okay, right? If validation fails, then the UE terminates decoding even before it is completed. Right? And the reason is, what is the reason? Okay, that it has to basically make these 36 attempts. Okay, and if it is not its DCI, why completely decode the DCI? Do the early termination. Okay, that's the key idea. Okay, right? If this CRC bit depend on some other bits, you will not be able to do this. You will not be able to do this early decoding. Okay, we want to understand this better. Read this carefully. I am giving you a broad idea why it is done like that. Okay, right? You understand it? Okay, what is happening here? So this bit, this CRC bit depends only on these bits. As soon as this is decoded, right, you can validate it and unscramble it and then validate it. Okay, if it doesn't, if it fails, then you decode, stop the decoding. Okay, right? So this is how it works. But now I'll tell you how this interleaver is implemented. Okay, right? This is a key feature. Let's understand this, how it is implemented. Okay, so the interleaver is activated through this flag IL, okay, and used only for downlink. Another key aspect, blind decoding happens only for downlink. Why doesn't it happen for uplink? Because base station only schedules the user, right? It exactly knows where the information is going to flow. It is not it's just that the user who is not aware of where its DCI is going to come, right? So this interleaver is only there for the downlink. If you read the code carefully, you'll see that, or the standard carefully. Okay, DCI length is between 12 to 140. Okay, right? So DCI length with CRC, how much will it be? A plus L will be between 36 to 164, and that needs to be interleaved, right? You see this length can vary between 36 to 164. Okay, now maximum number of bits which need to be interleaved is 164. Okay, now this, what am I saying here? This is called mother CRC interleaving pattern. Okay, right? What am I saying here? This interleaving pattern. Okay, what is interleaving? You take one bit, write it at a different position. That's what happens, right? Okay, that's what is interleaving. Okay, you go back and see what is happening here. You take this bit and you're writing it at a different position. You take this bit, write it at a different position. Okay, somebody should decide it for you. Okay, somebody should give you that pattern. Where should you write this input bit and the output? Okay, that pattern is called the interleaver pattern. Okay, and what we are saying here is that because this input can vary from 36 to 164, right? Okay, so you'll have to define so many patterns, right? From 36 to 164. It is something similar to what we do for forward error correction. You have the polar encoder only for one rate, right? Okay, then you match it. Okay, but the rate which you generate is called the mother code rate. Similarly, this pattern is called the mother pattern. Okay, from where you generate all other patterns, and the mother pattern is of the length, maximum length 164 bit. I'll show you how it is generated. Okay, and this, okay, all interleaver pattern for lower k values are derived from this mother pattern. Okay, why it's called mother we understand now. Okay, this is the pattern which is given in the standard. Just lifted it for you. What is the length of this? 164. Okay, right, and the bold bits are CRC bits. Fine. Okay, 24 are CRC, 140 is the message bit. Okay, but this is what is defined. Okay, you cannot keep storing so many interleaver patterns. Okay, right. So what you do is store this and then calculate other patterns. And a very simple formula. That's what we are going to discuss now. We understand this is a mother pattern. Okay, right. Let's see that, and this is what is this? Pi is the interleaver pattern. Okay, and then this is basically interleaver, and this is a maximum. That's what the notation says. Taken right from the standard. So what are we doing here? We know this pattern. Okay, and we have input is of a different length k. Okay, what is this slide telling you? The slide is telling you algorithm to generate smaller pattern from the mother pattern. Okay, fine. Very simple algorithm. Number of interleaved bit is upper bounded by 164. What are we calling it as? K interleaved max. K is the input. Okay, max is the maximum number of input bit which can go inside the interleaver, denoted as 164, right? Okay, fine. This is max. Okay, but the actual input size is capital K. Correct? We are feeding in A plus L. That is what we are calling as K. Correct? Okay, so the parameter h, I am defining a new parameter h. Okay, I have to calculate how much length, what should be the length of the interleaver K, right? But I have only this length. Okay, so how will I do that? I'll define this parameter h. Okay, what am I doing here? I'll take this 164, I'll subtract k from it. Okay, let's do that. Okay, I'll give you an example also. Now this element of this, what is this pi L max? This is that interleaver pattern which I gave to you, right? And where, look at this, what numbers are there in this? Numbers running from 0 to 163, correct? Because it is an interleaver, it is only gives you the locations, correct? Okay, and how much are the maximum location? 164 location, and they are the interleaved locations, correct? Okay, so there are these numbers from 0 to 163 over here. Okay, right? So what am I doing here? I'm calculating this parameter h. Okay, this is a recipe. I'll take an example, it will become more clear to you what we are doing here. Okay, so element of this mother code interleaver, mother interleaver is compared with this h. What will be this h? It will be some number between what? Okay, it will be some number. What is it? 164 minus, let's say, length is 24. Okay, or let's say 60. Okay, k is A plus L is 60. Okay, so what will it be? 86. Okay, so again some number between, it will be number lesser than 164 or 163. Okay, right? So they are compared with h. In case they are larger, they are stored in this pattern which you are designing, right? Let's see this. What do you do after this? Again, be patient, and with an example it will become more clear. So what is happening? Then from this pattern, h is subtracted from the entries such that it contains integers smaller than k in this permuted order. Okay, let's see this. Okay, our earlier example is this. Okay, once I give you this example, then all these steps will become clear what is happening here. Okay, what is h? What did we do with h? KIL is 164. K is 12 plus 24, right? 12 input bit and 4 CRC. What do you get? 128 number. Correct? Now what is this? Is 128. What is the second step? What does the pi L max contain? Number between 0 to 163. So I'll subtract this 128 from 0 to 163. All these numbers, that's what I'm doing. Elements of pi L are compared with H, okay, right? In case they are larger, they are stored in pi. How many such numbers will be there? How many are these numbers? It will be 36, right? How many numbers will be greater than 128? 36, right? That's the length. That's what is happening. That's the second step which is happening over here. It will give you exactly how many numbers after this comparison. Now it's clear what we are saying here, okay, right? But these entries are 129, 132, you don't want them. You want 32 and you want 36 entries, but their indices should be between 0 to 35. Because these are the location you have. These are the location you want to interleave. What do? You subtract H from it. That's what we are doing. H is subtracted from entries of pi. What do you get over here? Interleave sequence. Look at all these entries. What are they running from? They are running from 0 to 35. This is the recipe. Fine. Okay. Take time to digest it. This is, the first step is giving you a number. Second step will give you a number, give you all those numbers which are greater than 128. Correct? Because that's what you are doing. In their case, they are larger. They are stored in pi. Because you need those many 36 numbers. Correct? Or the length of the interleaver should be 36. Okay. Now, but these are not the right indices. So you subtract H from it and you get the desired indices. They are the indices which you want. They are the interleave sequence. So what you have by this doing this small exercise is that you get an interleaver sequence which has the right length and the right indices. That's all. Over. Right? Okay. So you can do this exercise for any length. It's fairly generic. The algorithm is generic. Okay. It will work for any length. Okay. Now that you have the interleave sequence, what happens after that? It's only the writing operation. Okay. So this interleaver consists of two steps. First, generating the right interleaver. Second one is basically writing that into the correct indices. Let's see that. Okay. So the interleaved bits from CRC block were called C0 to CK-1. Remember that? Okay. Bit output from CRC interleaver are called C0 dash to CK. The dash is appended. Okay. So what is this? Interleaved sequence will be what? How are you interleaving? Okay. You are taking this bit from the pi k and writing it as kth position. That's what you are doing. Okay. Pi of 0 will become C of 0. Please understand that. Okay. Let's see this. This is an interleaver sequence for our earlier example. We just derived it. Okay. This is an example. Let's see how it is working. Let's apply it to this, right? That's the example we have been taking. Okay. Right. So what is happening here? Okay. Look at this. See, this is pi of, what is pi of k is 0, right? Okay. Pi of 0 is what? 1, right? So first bit is written at the 0th position. That's what is happening, right? Okay. Then what is pi of 4? The k is 1, that becomes 4, right? So the fourth bit is being written at the first position. Do this for another one. This is pi of 2, this becomes 6. A6 is written at third position. That's what is happening. That's how it is interleaved. Right? Okay. Understand this. This is only the writing part. Okay. What will you do at the receiver? Do the reverse operation. Correct? Okay. And as I said, never search the standard for the receiver. Okay. You have to do this operation yourself. All of us are very familiar with this aspect now. But what am I saying here? What is the key aspect here? That what are we doing? The key idea was that this bit, okay, this CRC bit has been generated using these message bits, okay, and these message bits come before this CRC bits. And why is it there? So that it can help in the early termination of the polar decoding, okay. And why do you need this? So that you can save on energy, okay, right? And the bigger aspect is, why is all this done? To reduce the complexity of the blind decoding. The user has to basically do this multiple times, okay, depending on subcarrier spacing. It has to do 36 times. If you keep doing it, then it's a waste of energy, not even required. Okay. This is a philosophy. Okay. All this control chain, we have always been talking about the reduction in complexity, and we know why. Okay. This is one key aspect. Okay. Other key aspect which we learned in these classes are the polar decoding. Okay. And that works well for lower code block length, okay, which is in case of DCI is much lesser than the PDCCH. Okay. Right. So with these ideas in mind, we'll stop here. We'll continue discussing these ideas in the next class also. Okay. Thank you.